Implicit differentiation. Let's take a look at the chain rule before we do implicit differentiation. So the chain rule says if you want to take the derivative of a composite function, right? And I'm going to highlight this g, right? That's the inner function. There it is again. You've got to take the derivative of the outer function. Its variable will be the inner function. And then, of course, don't forget to multiply it by the derivative of the inner function, okay? So g of x is the inner function, f of x, or f of anything really, is the outer function. And then it's the derivative of f with the g of x still inside times g prime of x. Okay, so we're going to use that. We need to know that very well so that we can do implicit differentiation. So what I'm going to do is I'm going to do two problems, right? So I'm going to do this chain rule problem here, and then we're going to do the exact same problem again implicitly. Okay, so we're going to do chain rule first, then the implicit. So watch on the left, and then when I go to do a slightly different problem, but it should work exactly or very similar, you'll be able to compare the two and understand that implicit differentiation is just the chain rule with a couple other differences. Okay, so another thing we're going to do is talk about a little notation change. So normally I just write y prime here, right? I just write y prime. But when I'm taking the derivative, well, what I'm going to do is I'm actually going to use a slightly different notation. I'm going to actually take the derivative with respect to x of y, okay? And over here, I'm going to do the same thing. It's not very pretty here because I'm squeezing it in, okay? But I'm going to take the derivative of this with respect to y, all right? I think I'll just write that on a new line. So I'm going to take the derivative of something, in this case y, with respect to x. And of course, that's going to be dy dx on this left side, and that's why we write y prime, right? So we usually write y prime, but it really means this, right? The derivative of y. And if I do this to one side, I've got to do it to the other side. So I'm going to do it to this side as well. Okay, and we're going to get the derivative of all this. Okay. All right, so in the next line, then, instead of writing y prime, I'm just going to get, I get dy dx. All right, we're going to actually talk about that in a second because I did something here that I'm also going to do in the next column. All right, now, when I take the derivative of this, you know how to do this already, right? So the first one here, easy, it's just going to be, what, 6x cubed, right? So bring the 3 down, 6x squared, excuse me. Now here, we've got to do the chain rule. And that's really important. So you can see you've got this inner function here. Oh, no, I just wanted to use yellow. You've got this inner function here. And that's the same as g up here. So watch what we're going to do. I'm going to do this. I'm going to take the derivative of f, put g of x inside of its variable, and then I'm going to multiply it by g prime of x, right? So here it is. Take a look. And maybe I'll use purple here, right? So I'm going to do this. F prime of something, right? F prime of something, okay? So here's f, right? F is 4 times something squared. That's what f is. Not f prime, but f, right? 4 times something squared. 4, really, not times, I'm sorry, but 4, it is times, but I'm saying this is of something squared, right? So it's going to be 4, leave g, see there it is, leave g alone. So I'm going to put g back in here. I'm sorry, not 4, it's going to be 8. Leave g in here to the first power, right? So that's what all this purple is here, right? And then, of course, I'm going to put x squared minus 1 in here. I'm going to leave it in there. That's still g, right? That's still g, so I haven't changed that. That's still g. And then if you go back up here, we have to multiply it by g prime of x, okay? So here's g, right? That's g. So g prime of x is going to be 2x. 2x. And that is the derivative of g, right? Which I previously highlighted in blue. Okay, so this should come as no surprise. I'm just implementing here this chain rule that you see here, right? So it's f prime 8 to the 1, 8 something to the first, and that something is g of x times g prime of x, okay? And you can distribute and keep going, and I would normally, but I'm going to actually leave it here because that's all I need to know in order to do implicit differentiation, okay? So what makes the implicit differentiation different? So what makes it different is the problem doesn't have this thing, this g, okay? Or it does, but it doesn't have it in terms of x, right? So I'm just going to use z. I use the letter z. I don't want to use g. I like z better. But it's the same thing. It's as if I had put g in here, right? It's g of x. So here it is. This is the inside, okay? So, I mean, I'm calling it z. You'll see why in a little while, but oops, that's not what I want. I'm calling it z, but it's really, this is really like g. So here it is, okay? So I still have a composite function. So the f part is the 4, right? Is this 4 something squared, right? That's f. And then it's a composite function, so it's f, right? F of g of x, and here's the g of x. So exactly what I did here over here in the chain rule, exactly what I did in the chain rule over here, I'm going to do on the right side. Right? So let's go through it. So I'm going to ddx both sides, right? So I'm just going to write the result of it. I'm not going to actually write it, but you know, you could ddx this side, which means takes the derivative with respect to x, and I'm going to ddx this side and take this side with respect to x, the derivative. I'm not going to show that. I'm just going to show the result, okay? So the result is dy dx equals, now this is what you always know, 6 x squared, which is no different from over here, right? No different from over here, but watch what's going to happen. So the same thing I just did, if you look back over here, I did 8 something to the first power, right? So I'm going to do that. So plus 8 something to the first power, okay? Only this is going to remain z. And then normally, I would do the chain rule, right? So over here, we got 2x. Why did I do 2x? Because it's g prime of x, right? Or actually, if you want to think about it, it's dg dx, right? It's dg dx. We don't usually write it that way for the chain rule, but that's what this is, dg dx. So this thing here, right? This thing here, so that was g, and this is dg dx, okay? So in my problem here, though, I'm the only, unless you have a cat that walks all over this.
It's the D.R.E. Dr. Dre. You know I'm mobbing with the D.O.G.
Okay, we're back. So what we were talking about was taking the derivative of this. So normally we would put dg dx, right? Or as we called it here, g prime, whatever it is, it's the derivative of the inside, right? So it's, in this case, it's the derivative of z. But I don't know what z is. In other words, I don't know that z is this, x squared minus 1, so I can't put 2x like I did over here. So all I can do is leave it symbolically. Okay? So it may be, as in this case, right? It may be that z is equal to x squared minus 1, as you can see on the left side. And it may be that dz dx, right, is equal to 2x, but I don't know. And so I just leave it like this. And that's implicit differentiation. It's not much more complicated than that. So again, the final answer would just be 8z dz dx. Okay? Now, what's funny is that actually happened on the right side. In other words, when I did this, when I did a d dx over here, I mean on the left side, excuse me. When I did a d dx on the left side, I took the derivative of y with respect to x, right? And so I got 1y to the 0 dy dx. See? So in other words, this whole thing just becomes the number 1, right? And then the chain rule is dy dx. Now you're like, why are you using a chain rule here, right? Well, because I had y to the first, see? And I took the derivative of this. And because this is not plain old x, it's not plain old x, right? I had to do 1y to the 0, then take the derivative of the inside, imagine there's a parentheses here, and get dy dx. Okay, so compare these two, and you'll see it's really the same work. It's just that I can't represent this with an expression because I just don't know what z is in terms of x. So let's do another problem. Let's take a function. Now, this function is going to be definitely not explicitly given, right? So and I think it's very familiar to you, okay? Okay. You can't express this easily, not without a plus and minus, and that wouldn't really be a function. I can't express this in terms of y. I can't have something y equals something. It's just not going to work, okay? So when I have this implicit function, or it's not really a function, but this implicit expression, then I have to do implicit differentiation. Now notice again, this is where I can't just write y prime, right? There's no y equals here. So I'm going to have to take the derivative of this thing with respect to x. Of the whole side on this side, and the derivative with respect to x on this side. Okay? All right, now, the derivative with respect to x of x squared, right, is, and imagine there's a parentheses around this. Maybe I'll put the parentheses in a different color. There's parentheses around this, okay? So it's 2 parentheses, leave the x inside, close the parentheses, to the first power. And then, if I think about it, I want to take the derivative of the inside, right? Like it's a chain rule. And normally we would just say it's 1. You're right, it's 1. It's derivative of x with respect to x, right? So it's the derivative of x with respect to x. See, if I do every parentheses this way, it'll work. Now let's go to this next term here, right? So we'll put a parentheses around here. Okay, so take the derivative of this with respect to x. So it's also 2 something, right? In this case, it's y, 2y to the first power, and then times the derivative of the inside. Now, you're normally saying, well, unless this is complicated, I don't have to worry about chain rule. Well, we're going to chain rule every single time, right? Every single time. So the derivative of y with respect to x, right? In other words, let me show you over here. The derivative with respect to x of y, okay, is dy dx. Just dy dx. So this is dy dx, okay? Equals, now the derivative of a constant, I don't care with respect to what, it doesn't matter. This is not changing, constants don't change, so it's 0. Okay? Now, the whole thing here is a couple things. The whole thing is here, I'm looking to solve for this, right? That's what I want, because ultimately, I didn't write the question here, but, and I'll add it here. The question should have been, find the slope. Okay, find the slope. And you know, slope is delta y over delta x, and of course this is the derivative. So in order to get this, I have to do this. I have to dx both sides of the equation. That means take the derivative of this mess with respect to x. Right? In a second, I'll do it with respect to y to kind of show you the difference. Okay. Now, you have to, the other thing I want to show you, of course, is that something goes away really quickly. You don't really need to write it, but I kind of recommend that you do for a while so that every variable gets this, right? We've been doing this, we just haven't been writing it, okay? What is the change of x with respect to x? And if you remember my chain rule lesson, how much time does it take for me to take a test compared to how long it takes for me to take a test? Well, that's silly. Anything compared to itself is always the same, right? So that whole expression there just goes to 1. So you can write it if you want. This way you're always doing implicit differentiation every time, or really the chain rule. But it goes away. So I get 2x plus 2y dy dx equals 0. Okay, and remember, I'm trying to solve for this. I'm trying to solve for this. So I'm going to subtract 2x from both sides, and then I'm going to divide by 2y. I'm not going to show you all that work just to save a little time, right? So I'm going to subtract 2x from both sides. Okay, and then I'm going to divide by 2y because this dy dx is being multiplied by 2y. All right, and my final answer is dy dx equals negative x over y. All right, we're going to come back and look at that because this is the derivative of a circle with a radius of 5. Actually, it's the derivative of any circle centered at 0, 0. Right? And of course, derivative is slope. So it's the slope of a circle centered at 0, 0 of really any radius. Doesn't matter because this 25 up here wouldn't make any difference because the derivative is 0. And we're going to look at that in class tomorrow, and we're going to actually test it out. We're going to plug in some x and y values and talk about why there has to be a y. So with implicit differentiation, another thing to notice is that there's often a y in my answer, right? It's not just a function of x, the derivative. The derivative, the first derivative here, is not just a function of x, it's a function of multiple variables. Okay, so I think this might clear it up if I try to tell you that sometimes I take the derivative with respect to other variables. So I'm going to take the exact same function. And now someone might say, what would be the derivative of y with respect to t? Okay. What would the derivative of y be with respect to t? There is no t in this problem, and that's okay, right? It's not, before we were doing dy dx, and there was an x in the problem, so you're going to get that 1, but this one is not going to happen. So what I'm going to do is take d dt of both sides. Okay, put a bracket here. Okay, so let's try it. So how do I do the derivative? Well, this is some quantity squared, right? So it's the sum quantity, there it is, x squared, so it's 2x to the first, times what? Times the derivative of x with respect to t, right? In other words, the chain rule, so the derivative of this. But it's not dx dx, right? So it's dx dt, okay? Because this bottom is dt. And the next one is plus, keep the color code the same, 2 to the first, right, of y, and it's dy dt equals 0, okay? So now if you want to solve for dy dt, you're going to have to subtract this whole mess, okay? And then you're going to divide by 2y. And you're basically going to get 2x divided by 2y, sorry, negative 2x divided by 2y, so it's going to be negative x over y times dx dt. So you're going to have a rate in terms of another rate. And then the last thing I'll do is I'll do the same thing except with respect to y. Okay, now, somebody, it's kind of rare, but somebody might ask for the change in x compared to the change in y. Okay? And if I did that to my expression, okay, I'm going to get on the right side, I'm going to get 0, we know that already. And for this expression, the circle, I'm going to get 2x, right? So 2x to the first times the derivative of this inside. See, I'm always doing the derivative of the inside of it. I'm forgetting, I'm not caring what variable it is. Normally, we would only care about the variables that aren't this variable, okay? But I have to do it every time. So it's dx, so it's d of x, so it's dx dy, the change in x over change in y. And then this one becomes 2y to the first, and then that variable gets a dy with respect to y. Again, notice this is very important. The bottom is y, so all of these are dy's, okay? Of course, this one goes to 1, which is nice. So what's left here is 2x dx dy equals 2y. I'm sorry, not equals, plus 2y equals 0. And I can subtract 2y from both sides, so I'm going to get a minus 2y over here, and then I'm going to divide by 2x, right, over 2x. And so dx dy equals, we're going to reduce this, negative y over x. Obviously, that's just the reciprocal of what we did on the previous page. I don't think it's on this page. And that's it. Okay, so let's give you one problem to try. So I want you to do this problem two ways, actually. I want you to do this. Okay, I'd like you to tell me, based on this equation, what is dy dx? Okay, and then I'd like you over here to do it explicitly. So this is implicit. And I'd like you to do this explicit. Okay, so I'd like you to, one, I'm not going to show you, but I want you to solve for y, because this can be written explicitly. A lot of functions can't be. The circle you just saw can't be written explicitly. But this function can be written explicitly. In other words, solve for y, get y by itself. And then take the derivative normally. Okay, and then compare your answers. So compare your answers from both problems, right? In both problems, you're going to get dy dx equals, right? That's what I'm asking you for. dy dx equals, dy dx equals. Okay, and let's see what you come up with. So try implicit differentiation here on this guy on the left. And then in this case over here, do it explicitly. So solve for y, get y by itself, take the derivative like you're used to doing, and see if you get the same answer.